Correlation with two variables. Co means two, and relation is the relationship between those two things. If we're talking about the age of salmon and the length of salmon, here's a salmon. That's pretty old, so it's pretty big. The older the salmon, the longer the salmon. There's a correlation between the length of the salmon and the age of the salmon. Or if you're talking about the distance traveled in an electric car. In an electric car, the more electricity used, the greater the distance you travel, or the greater distance traveled, the more electricity you've used. Correlation. When we talk about type, direction, we have linear and nonlinear. The direction could be positive or it could be negative. The intensity. So we could have zero intensity. Weak, we have moderate, we have strong, and we have perfect. Perfect is if like there's 100% correlation. And we'll talk about that further. The direction could be positive. That means the variables both increase or they both decrease. Or it could be negative, where one is increasing, the other is decreasing. If the correlation coefficient is zero, then the intensity is zero. If the correlation coefficient is anything less than, let's say, 0.625, it's weak. If we're talking about anything over 0.625 or equal to 0.625, less than or equal to 0.81, then it's moderate. If it's anything greater than 0.81 and less than 1, it's strong. But if it's 1, it's perfect. For it to be perfect, it means it's on a line. It's all following a line. They're all collinear. A contingency table. A contingency table is used to visually see the relationship between two variables. Here is a two-variable distribution representing the age and number of branches of 18 trees of the same species. You got X is the age of the tree, Y is the number of branches. The age in years, Y is the number of branches. We're going from the age in years. The lowest value we have is 12. The biggest number we have is 33. You always want to go up by ones, twos, or fives, or powers of 10 times that. 10, 20s, or 50s, or 100s, 200s, 500s. You don't want to go up by threes, you don't want to go up by fours, you want to go up by ones, twos, or fives. We're going up by fives. I'm looking at 10 to 15 years, and then we're going to 15 to 20 years. Now this is between, like 10 is included here, 15 is not included. That's 10 to 14.999999, not quite 15. This is from 15 to 20, then 20 to 25, 25 to 30, 30 to 35. The highest number we have is 33, which is in here. The number of branches. What's the smallest number of branches we have? 145. We don't have anything less than 100. I'm going to start at 100 and I'm going to go up by 100. I'm going up by ones. Think of it that way. 1 times a power of 10. 100. We want to go up by either ones, twos, or fives, which is 10s, 20s, 50s, or 100s, 200s, 500. I'm going up by 100, and we're looking at between 100 and 200. What I'm going to do is make a tally table first. This is the precursor to the contingency table, is a tally table. I'm going to count this 12-year-old tree. It has 160 branches. 160 is between 100 and 200. I'm going to put a little 1 here. I'm going to cross it off here, put a 1 here. Cross up the 13,145, which also falls in right here. I'm going to cross it off, put another 1. Then 13 and 220. Well, 13 and 220 is going to fall in here. So I'm going to put a little, cross it off, put a 1. Cross this 1 off, 15 and 240. 15 falls in here. 240 falls in here. I'm going to put a little 1 right there once I cross it off. 16 and 205. 16, 205 is going to fall in right here. Cross it off and then put a little 1 there. 20 to 25. The next one, 19, 285. The 19 falls in here. 285 falls in here. I'm going to cross it off and put another 1 there. Then 21, 390. 21 is down here. 390 is going to fall in right there. Cross it off and put a 1 right there. Then 220, 410. Cross it off. 410 is right in here. Then 222, 350. 22 falls between 20 and 25. 350 falls in right here. I'm going to put a little, cross it off and put a little 1 there. 23, 360. 23, 360 falls in here. Cross it off, put another 1 right there. 24, 325. 24, 325 is going to fall in here. Cross it off, put another 1 there. 25, 455. 25 is here. 455 is up here. Cross it off, put a 1 right there. 27, 320. 27, 320 falls in right here. Cross it, put a 1 right there. 27, 475. 27 falls in here. 475 falls in here. Cross it, put a 1 right there. 27, 410. 27, 410 is also going to fall in right here. Cross it off, put a 1 there. 29, 410 falls here again. Then 30, 555. 30 is down here. 555 is right there. Then 33, 530. 33, 530. We're going to put another 1 right here. Cross it off, put another 1 right there, and we're done. This is our tally table. The contingency table is you're just going to represent this tally table with numbers. I'm going to do the same thing. Instead of writing a Roman 2, 1, 1, I'm just going to put the numbers in. So 2, 0, 0, 0. Then you want to add these all up. Okay, so that's going to be our totals here. So this is going to be a 3. Anyway, so this is 0, 3. We fill all these in. Then we add up our total. I'm going to add up all the columns. 4 and 1 is 5. 1 and 4 is 5. The totals, we have 1 and 4 is 5. 4 and 1 is 5. 0 and 2 is 2. The totals of the rows, 2 and 1 is 3. 3 and 0 is 3. 1 and 4 is 5. 1 and 4 is 5 again. 0 and 2 is 2. If you add all of these up, it should be 18. 3 and 3 is 6, plus 5 is 11, plus 5 is 16, plus 2 is 18. Here, 2 and 4 is 6, plus 5 is 11, plus 5 is 16, plus 2 is also 18. This is 18. It's a total of these classes and a total of those. Notice all the data, wherever we have data values, it describes a diagonal here. Because we have this nice strong diagonal, we can say that this is linearly related. If it wasn't linear related, we wouldn't have this nice diagonal in the center. This is my independent variable. My x's go here. My dependent variables go across the top, across here. These are the dependent variables. These are called the classes. These are the little ranges, 10 to 15, 15 to 20. These are called classes as well. These classes are these. Then these classes are the 100 to 200, the 200 to 300, and so on. These down here are the frequencies of the classes. Here are the frequencies of those classes. The total data points, 18. Correlation. This is linear correlation, and we can tell because we have this nice diagonal that I was talking about before. It's either going to be a diagonal this way, or it can be a diagonal going that way. That's not what we have here, but it could be. And if you do, then you have a nice linear correlation. You want to either go up by 1s, 2s, or 5s, or 10s, 20s, 50s, or 100s, 200s, 500s. But it's always 1, 2s, or 5s, powers of 10 times that. Anything else is just going to be really awkward. It could also go up by powers of 10, like times 10 to the negative 1, by 0.1, 0.2, 0.5, and so on. This is the independent variable. This is your x values. This up here are your y values, or the dependent variable. These are called classes. The 10 to 15, the 15 to 20, the 20 to 25, the 25 to 30, 30 to 35, these are your classes. These are your classes for the dependent variable up here. The 100 to 200, 200 to 300, 300 to 400, 400 to 500, 500 to 600, these are your classes. These are the frequencies of the classes. So the frequencies of these classes are written down here, and these are the frequencies of classes, and these are the frequencies of these classes. This is the total number of data points, 18. Correlation, linear correlation, if there's a diagonal. We have a nice diagonal here. This is linear correlation. It's on the diagonal, either this way, like that, or that way. So this is linear correlation. When you're going up in your classes, here we're going up by 5s. You want to go up either by 1s, 2s, or 5s, or powers of 10 times that. 10, 20s, 50s, 100s, 200s, 500. Or you can go 0.1, 0.2, 0.5. Don't go up by 3s, don't go up by 4s, don't go up by 7s, don't go up by anything awkward, or 1.5s or 2.5s. Always go up by 1s, 2s, or 5s. It makes life a lot easier. I want to make a scatter plot from those data points. I need to label my axes. I have my x-axis and my y-axis, the age in years, number of branches. This is my y variable, and it's just a number, so I don't have to put a unit. This is the number of branches, and age is the name of the graph. You need to have a name of the graph. You need to label your axes. Then I'm going to plot these points. Notice I have the number 2 at 10, 15, and 100, 200. How many dots do I put? If you want, you can put 2 dots, but they're going to be right on top of each other. If you put 1 dot right here at 10, 15, 200, 300, which is here, I put this dot. So this 1 gets represented here. This 2 is only represented by 1 dot, or 2 dots on top of each other. We can't tell. Okay, that's my point. You put 1 dot per data point. This 3 is at 15, 20, 200, 300. 15, 20, 200, 300 is right here. We put 3 dots here. 1, 2, 3, but they're on top of each other. We can't really tell. We have a 4 at 15, 25, 300, 400, 20, 25 at 300, 400 right here. We're going to put a dot, or 4 dots, but they're on top of each other. We can't tell. Then we're going to put a dot at 20, 25, 400, 500 right here. 1 dot. We're going to put a dot at 25, 30, 1 dot at 300, 400. 25, 30, 300, 400, a dot here. Then we're going to put 4 dots right here at 25, 30, 400, 500. 1, 2, 3, 4 right here. Then at the next level is 30, 35. We're going to put 2 dots at 500 to 600 right here. 2 dots at the top, but they're on top of each other. Think of it that way. or just put one dot. This is our scatter plot. In this scatter plot, you might want to find the correlation coefficient, build a rectangle around these things, measure the length of the rectangle. That gives us 10.4 centimeters. Then we would measure the width, which is 2.6 centimeters. Then we could find our correlation coefficient, 1 minus 2.6 divided by 10.4, which is 0.75, which is moderate. And it's positive. We have a positive slope. Here we're looking at the average height of men in France between 1880 and 1960. Here's our data. In 1880, the average height of dudes in France was 169 centimeters, but by 1960, it was 177.1 centimeter. Let's make a tally table. I'm going to put the year. This is the independent variable, and I'm going to put the dependent variable, the height, up here. The height depends on the year. We're looking at between 1880 and 1900. I'm going up by 20s. 1880 to 1900, 1900 to 1920, 1920 to 1940, 1940 to 1960, 1960 to 1980. We're looking at the heights of people. We're looking at 165 to 170, 170 to 175, 175 to 180, and that encompasses all the data. Always trying to go up by 5s when you can, but going up by 10s, going up by 20s. So 1s, 2s, or 5s. Here we're going up by 20s. 1880, we had 169. 1880 is in here. 169 is right here. I put 1 there. Then we have, cross that off. Then 1890 is 169. 1890 is in here as well. 169 is another one right here. Cross that off. Then 1900, we have 170.4. That brings us down here. 170.4 is going to be right in here. Cross it off, put a 1. Then 1910, it's going to be still within here. We're 171, so we put another 1 right there. Then 1920, it's 171. 1920 is down here. 171 is right here. Then 1930, we have 172.8. 172.8 is right here as well. Then we have 1938, which is still in this row, is 173.8. 173.8 is within this realm right here. Cross it off, put another 1 right there. 1956 is 176. 1956, we're between 1940 and 1960. Here we are. Then 1960, we're at 177.1. 177.1 is down here. We have another 1 there. Then we can build our contingency table by filling in the same things, but we're just going to put numbers where our tallies are. 2, 0, 0, 0, 0, 2, 3. Then the totals, 2 plus 3 is 5. Down here, 0, 0, 0, 1, 1. And that makes it 2 down here for the total. Totals across, we have 2, then 3, then 1, and 1. And what is that up to? 4 and 3 is 7, 8, 9. So there's 9 data points in total. 2 plus 5 is 7, plus 2 is 9. See, 9 and 9. Our total is 9 data points. Then we want to make a scatter plot based on that. My x's are starting at 1880. I'm putting these dates down. We have 1880 to 1900, 1900 to 1920, 1920 to 1940, 1940 to 1960, 1960 to 1980. For the heights, I have 165 to 170, 170 to 175, 175 to 180. I've got 2 at 165, 170 at 1880, 19. So right here, I've got 2 dots right here. Height in centimeters, years. The title of the graph is Scatter Plot of the Average Height of Men in France from 1880 to 1960. I've got 2 at 1880, 1900. 1880, 1900, 1880, 1900 at 165, 70. Right here, I've got 2 little dots on top of each other. Think of it that way. 2 dots here, or 1 dot if you like. The next one, I've got 2 dots at 1900 to 1920, corresponding to 170, 175. I'm putting 2 dots right here. I'm putting 3 dots at 1920 to 1940 and 170 to 175. 1920 to 1940, 170 to 175. I'm putting, think of it as 3 dots right on top of each other. We only see the 1 dot is my point. We have 1 dot at 1940, 1960, and that is 175, 180. 1940 to 160, 175 to 180. Put a dot here. Then 1960 to 1980, we have 1 dot at 175 to 180 right here. So this is our scatter plot. We could draw a rectangle of best fit around the data points and then measure them using a ruler. This is 9 centimeters, and measuring this way, we get 1 centimeter. Our correlation coefficient would be r is equal to 1 minus 1 over 9, which is 0.8 repeating. This is a strong correlation. That's strong, and it has a positive correlation.